Welcome to AI Paper Slop. Today we are unpacking Sparse Delta Memory, scaling the state of linear RNNs through sparsity. This is from Loic Caban and the research teams at Metafair, Indomaria, and the University of Tübingen, published on July 9, 2026. So if you're building agentic workflows, long context models, or, video architectures, you already know the fundamental mathematical wall we're hitting. Standard transformers have this unbounded O of TKV cache, so the memory bottleneck is linear and just brutal.
Yeah, it really is.
Right. And linear RNNs like Mamba or Gated DeltaNet solve this by compressing the pass into a fixed size hidden state. But they suffer on long context recall because their state size is simply too small. So this paper introduces Sparse Delta Memory, or SDM. The researchers basically replaced the dense key-value outer product found in gated DeltaNets with sparse reads and writes to a massive explicit memory table using a product P memory indexing trick.
Which is just a brilliant workaround, honestly.
Totally. The result is a hidden state thousands of times larger, matching the exact same FLOPs and parameter count as a dense RNN.
Yeah.
And at the 8 billion parameter scale, SDM not only crushes other RNNs, it actually beats full attention models on short context and several long context tasks.
Right, which is just a remarkable engineering feat because it effectively keeps the constant memory benefits of recurrent neural networks without incurring that catastrophic recall penalty we've come to expect.
Yeah.
I mean, to really appreciate why SDM is such a breakthrough for the field, we have to look closely at the mechanics of the attention versus recurrence bottleneck.
Yeah, exactly. The fundamental math problem.
Exactly. The issue with standard softmax attention is that you are storing every single token's key and value vector in the KV cache. So if your sequence length is, say, 100,000 tokens, you are caching 100,000 vectors.
Per layer, per head, it just explodes. It's like packing for a trip using a massive U-Haul. You never forget anything because every single item you own is in the back, but actually driving that U-Haul gets exponentially slower and more expensive as you add more stuff.
That is a perfect analogy.
Unbounded growth just kills efficiency for large code bases or, long horizon agentic loops where the model needs to run continuously. So the alternative the industry pivoted to is the linear RNN. It uses a carry-on bag. It's incredibly fast. The size is constant regardless of how far you travel, but you are definitely leaving your winter coat behind. You are forced to throw away information to fit into that fixed state.
Right. The carry-on analogy captures the limitation beautifully, and this was actually rigorously formalized in a recent paper by Aurora and colleagues. They demonstrated mathematically that long context performance in these recurrent models is fundamentally bounded by the hidden state size.
Right. Like if there's no room in the bag, you can't pack it.
Precisely. A neural network simply cannot recall what it does not have the physical tensor capacity to store. The obvious engineering answer seems to be, well, just make the RNN memory size bigger, buy a bigger carry-on. But that is where modern linear RNNs, whether it's Mamba 2 or the Gated DeltaNet, which we often just call GDN, hit a compute wall based on their update mechanisms.
Because they rely on dense state updates. Right. And when you say dense, we are talking about applying an operation to every single parameter in the state matrix for every single token.
Yeah, that is the core bottleneck right there. In a model like GDN, your state is a dense matrix. Every time the model processes a new token, it applies a decay factor to the entire matrix to forget old information, and then adds a new delta update to the entire matrix.
Which is insanely expensive.
It is. The per token computational cost of this dense operation is O of the query key dimension times the Goyo dimension. So in a standard GDN, these might be 64 and 128.
So if you try to scale up the size of that state matrix to hold more information, say you're trying to match the capacity of a transformer's KV cache, you have to massively increase those dimensions.
Right. And because the update is a dense outer product, your FLOPs, your floating point operations per second, increase linearly with that expansion. Scaling the state by a factor of 1,000 means your compute cost goes up by a factor of 1,000.
Wow, which completely defeats the purpose.
Exactly. It becomes prohibitively expensive, erasing the inference efficiency that made you want to use an RNN instead of a transformer in the first place.
So we need a bigger carry-on bag, but we refuse to pay for extra baggage fees. We need more state capacity without requiring more compute. And the solution this paper proposes is sparsity.
Sparsity is the magic word here, yeah.
Instead of applying the decay and the delta update to the entire dense state matrix, SDM maintains an explicit memory table with a massive number of slots, which they call N.
Right, because the researchers observed that the GDN update rule is practically begging to be sparsified. GDN uses a forget gate to decay old associations and an input gate to write new ones. But, you don't actually need to update every single concept in your memory when you read a new word.
Right.
If you are processing a token about apples, you don't need to update your memory about astrophysics. SDM takes advantage of this by applying the gated delta update to only a small selected number of slots in that massive n-slot memory table. The unselected slots simply remain completely unchanged for that token step.
Okay, let's unpack this because this is where I need to push back on the compute cost on behalf of the engineers listening. If we have n slots in this explicit memory, say, 1,000,000 slots doesn't just scoring which slots to update require massive compute.
It sounds like it should, yeah.
Right. To figure out which slots are most relevant to apples, you have to calculate a similarity score for every single one of those 1,000,000 slots. Aren't we introducing an O of n operation just to find the indices? That seems like it would completely ruin our FLOP's budget.
You are identifying the exact trap that usually kills sparse architectures. If you compute a full, dense score vector of size n, you haven't saved any compute at all. But this is where the paper implements a product key memory, or PKM, indexing trick. It is a mathematically beautiful way to avoid materializing the full score matrix.
Oh, interesting. How does the math actually work?
Instead of projecting your input query into a single vector of size n, the PKM mechanism projects the pre-update, write keys, and read queries into two separate, much smaller halves. Each half is a vector of size square root of n.
Ah, wait, so if n is 1,000,000, the square root of 1,000,000 is just 1,000. So instead of a vector of 1,000,000, we have two vectors of size 1,000.
Exactly. You compute the scores for just those two small vectors. Then you take the outer sum of these two vectors to implicitly define the scores for all 1,000,000 slots. The genius of the PKM trick is that you can find the top W scores of an outer sum in O of square root of n time rather than O of n time.
Wow. Okay, let me make sure I'm visualizing this correctly. It's like trying to find the tallest people in a massive stadium without measuring every single person. If you arrange the stadium into a grid of rows and columns, and you know the height profile of the rows and the columns independently, you can find the absolute highest points in the grid just by looking at the intersections of the top rows and the top columns.
Yeah, that's it.
You never measure the 1,000,000 people in the middle.
That analogy maps perfectly to the math. The mathematical property holds that the top k elements of the outer sum of two vectors are entirely contained within the outer sum of their individual top k values. So you find the top values of your two 1,000-dimension vectors, and you only combine those specific high-scoring elements to find your final selected write and read indices in the 1,000,000 slot table.
That is incredibly elegant. So we get to select W write slots and R read slots out of a massive memory table, and the compute required to find them scales sublinearly.
Which leads directly to the strict isoFLOP and isoparameter design of their experiments. Because of the PKM trick, SDM's per token computational cost drops to O of W plus R times the value dimension. Notice that n, the total memory size, is completely absent from that complexity formula.
That's wild. So as long as we fix the number of sparse reads and writes, we can make the memory table itself as big as we want without changing the theoretical FLOPs per token.
Exactly. And to make it a perfectly fair fight against the baseline models, the researchers set the number of sparse writes, W, and the number of sparse reads, R, to 64. They chose 64 because that exactly matches the dense query key dimension used in the GDN baseline.
So it's a true one-to-one comparison.
Right. By matching that dimension with the number of sparse operations, the FLOPs match exactly. The number of parameters, specifically the linear projections for queries, keys, and values, also match exactly. So any performance improvement we see in SDM stems purely from having a larger memory capacity, not from throwing more compute at the problem.
And the capacity difference they achieve is staggering.
Yeah.
I mean, looking at Table 1 in the paper, they detail a scaling ladder. They train models from 257 million parameters all the way up to 8.14 billion parameters using a strict 160 tokens per parameter budget.
Which ensures they are evaluating everything in an inference optimal setting, mimicking how frontier models are trained today.
Right. And at that 8 billion scale, the SDM state size is nearly 8 gigabytes per layer. That amounts to 111% of model's non-embedding parameters. The memory state is literally larger than the model's weights.
It is a complete paradigm shift in how we allocate memory in recurrent architectures. We are moving from a world where the hidden state is a tiny bottleneck to a world where the state dwarfs the network itself. And because they locked in those isoFLOP constraints, we can really trust the performance data.
And the data is pretty definitive, isn't it?
Oh, absolutely. The power law scaling shown in Figure 3 of the paper is definitive. SDM consistently outperforms the dense GDN at every single level of compute. But what is truly remarkable is what happens when they scale up to 8 billion parameters. SDM reaches a significantly lower validation loss than the GDN, and it actually beats the full attention baseline.
A fixed-state recurrent model beating a full attention model is wild.
Yeah.
Let's look at the ruler benchmark for long context retrieval, because that's really where the rubber meets the road for these architectures. At the 8B scale, SDM scores a 50.2 on ruler, compared to GDN's 34.2. It crushes the dense RNN.
It really does.
But amazingly, SDM matches or beats full attention on 3 out of the 6 evaluated ruler tasks, including single 3 and variable tracking.
Yeah, and we see this same dominance translated to perplexity on code data, too. When they evaluated the models on documents stretching up to 1 million tokens, SDM's perplexity continually decreases down to around 2.0. Meanwhile, Mamba 2 and GDN flatline around 2.2 once they hit their capacity limit.
They literally run out of room in their carry-on bag while SDM just keeps packing.
Exact.
Here's where it gets really interesting. I want to ask this on behalf of the engineers listening. It is counterintuitive that a fixed-state model beats an infinite memory full attention model on tasks like variable tracking. I mean, with full attention, every variable ever mentioned is perfectly preserved in the KV cache, right? Nothing is compressed.
Right, that's the theory.
So why does SDM actually have an advantage here when it is fundamentally forced to discard information?
The advantage comes down to the mechanics of the delta rule combined with the forget gate. Think about how raw softmax attention works. It is essentially computing a massive weighted average over everything in the KV cache. As the context grows longer, the sheer volume of tokens acts as noise.
So it gets distracted.
Precisely. The attention mechanism can easily get distracted by irrelevant past tokens or outdated variable assignments. SDM, however, uses continuous targeted forgetting and writing. If a variable's value is updated in a codebase, the delta rule actively subtracts the old value from the specific memory slot and writes the new one.
So it's actively managing state transitions. Full attention is just passively accumulating a massive log of everything that ever happened, whereas SDM is acting more like a CPU register, overwriting the old data with the current state.
Yeah, the forget gate is actively decaying less relevant associations. SDM is dynamically filtering noise during inference. It is maintaining a clean, up-to-date working memory, which turns out to be much more effective for tracking variables over long horizons than searching through a massive noisy log.
That makes a lot of sense.
Yeah.
But SDM doesn't just dominate long context benchmarks. It actually beats full attention on short context and reasoning tasks, too. I'm looking at their scores on HelloSwag, ARC, and MMLU. Why would an architecture explicitly designed to solve long context memory bottlenecks boost general short context reasoning?
This brings us to what might be the most fascinating part of the architecture, the parametric memory, denoted as M0. Because the SDM state is so massive, nearly 8 gigabytes at the 8B scale, the researchers realized it doesn't have to start empty at the beginning of a sequence.
Oh, wow.
Right? They chose to treat the initial state of the memory, M0, as a learnable parameter during pre-training.
This is where my brain kind of melted reading this. A standard GDN is like a whiteboard. You have to wipe it completely clean every time you start a new sequence.
Yeah.
But SDM is like a massive library where the shelves already contain reference books learned during pre-training, and you're just adding post-it notes to those books during inference.
That is a brilliant way to conceptualize it. The ablation studies in the paper isolate this effect beautifully. They trained both SDM and GDN models with null initial states, blank whiteboards, and then with learned initial states.
And what happened?
Well, for GDN, learning M0 did absolutely nothing to improve performance. The negative log likelihood didn't budge. Its state is simply too small to hold meaningful world knowledge. Any pre-trained information gets overwritten almost immediately by the new context.
But for SDM, because it has millions of slots, it can dedicate some of them to static world knowledge while reserving others for dynamic context.
Exactly. The learned M0 dramatically improved short context negative log likelihood and reasoning accuracy for SDM. The model literally uses that massive initial state to store generalized knowledge learned during pre-training, giving it a massive head start on reasoning tasks before it even reads the first token of the prompt.
We should clarify, though, that the long context ruler gains came primarily from the sheer capacity of the memory during inference, not just the M0 initialization, correct?
Oh, absolutely. When they ablated the memory size, dropping it from 432 megabytes down to 27 megabytes, the long context recall degraded monotonically, regardless of M0, so we can cleanly separate the benefits. The short context reasoning boost comes from learning a massive M0 during pre-training, but the long context recall boost comes from having a massive N to dynamically write into during inference.
All right, theoretical FLOPs and benchmarks are great on paper, but for the ML engineers actually deploying this, what does this look like on hardware? Let's talk about model FLOPs utilization, or MFU. There is an unavoidable hardware bottleneck here, right? GDN's tiny state fits comfortably inside fast GPU RAM, but SDM's massive 8 gigabyte state has to live in high bandwidth memory, or HBM, which has roughly 10 times lower bandwidth.
Yeah, this is the classic trade-off with sparse memory models. Your theoretical compute is low, but your memory access latency is high. Moving data back and forth from HBM to the compute cores slows everything down.
Which hurts the MFU.
Right. The current SDM kernel MFU is indeed lower than the highly optimized GDN kernel from the FLA library. However, the Meta team used a very clever software engineering trick to mitigate this chunk-wise parallelism, specifically utilizing something called the WY representation.
I saw that mentioned in Section 6. The WY representation comes from the Woodbury matrix identity, right? How does that actually help us deal with the slow HBM?
The Woodbury matrix identity allows you to take a sequence of linear updates, which normally have to be computed one after the other, and rewrite them as a single block matrix operation. By using this representation, they can group the sequence of tokens into chunks. Within a single chunk, they resolve all the causal dependencies and local attention in the ultra-fast SRAM. They compute the net delta update for that entire chunk of tokens locally.
So instead of writing to the slow HBM memory for every single token, you batch all the computations within a chunk in the fast memory, calculate the final aggregated update, and then do a single sequential write to the HBM. You are essentially hiding the memory latency behind local compute.
Exactly. And because of this hybrid approach, the N10 training overhead is surprisingly modest. At the 8B scale, training SDM was only 1.49 times slower than GDN, despite the state being about 4,000 times larger.
That's practically negligible for that much capacity.
Right. And when you move to inference decoding, because SDM avoids the linear scaling of the KV cache, it is actually 6 times faster than full attention.
That is highly practical. It proves this isn't just a theoretical math trick, it's deployable. I also want to touch on the adaptive memory access patterns they observed. When they analyzed the softmax distributions over the read and write keys, they found a fascinating asymmetry. The writes are highly peaked. The top 32 keys capture about 85% of the probability mass, but the reads are much more uniform and broad.
This asymmetry highlights how the routing mechanism learns to optimize the latent memory space. When the model writes, it needs to be highly selective to avoid overwriting unrelated information. But when it reads, it casts a wider net to synthesize context.
That makes total sense.
What's incredible is how the model dynamically balances this based on its capacity constraints. If you restrict the number of reads by setting R to 32, the model compensates by making the writes more uniform, spreading the information out so it's easier to find later. If you give it abundant reads, say R equals 128, the writes become highly peaked and selective. It isn't randomly scattering data, it is actively organizing its own memory architecture based on the hardware constraints you give it.
So what does this all mean? To summarize, Sparse Delta Memory is a game changer because it bridges the seemingly impossible gap between the inference efficiency of linear RNNs and the massive recall capability of transformers. By keeping the compute constant, but scaling the state capacity by orders of magnitude through the PKM outer sum trick, it opens the door for true, long-term agentic memory. You get the inference speed of the carry-on bag, but the recall capacity of the U-Haul.
It fundamentally challenges the assumption that the field is stuck with the KV cache for complex, long-horizon tasks.
Which leaves us with a provocative thought to explore. We know SDM uses a massive parametric memory, M0, serving as pre-trained world knowledge. And we know it is updated locally via the delta rule during inference. Could we eventually persist those inference time updates back into the base model?
Oh, like actual continuous learning.
Exactly. Imagine a continuous learning robotic agent or a personal assistant that never resets its M0. It just seamlessly transitions from in-context learning to lifelong parametric learning, modifying its own weights in real time. What does an AI look like when its short-term working memory and long-term pre-trained memory become the exact same mathematical structure?
That is the exact horizon this architecture points toward. We are looking at the blurring of the line between static waits and dynamic activations.
Something to mull over until next time. Keep building, keep optimizing, and we will see you on the next deep dive.